Yeah, let's now take a look at two of the most common weight initialization schemes for deep neural networks. So the first one we start with is called Xavier-Glorot initialization. Sometimes people just say Xavier initialization. Sometimes people say Glorot initialization. So the fact or the name comes from the name of the first author of the paper that proposed this method. So usually this type of initialization is used in connection with a 10H function, the hyperbolic tangent activation function. And recall this is also a sigmoidal activation function, similar to the logistic sigmoid, except that the output is centered at 0. And so where we have in the logistic sigmoid something like this, I'm really not good at drawing this. Let's try again, where the output is at 0.5 for the logistic sigmoid. Then we have for the 10H something more like this, where we have 1 and -1 here. And if you recall, the partial derivative of that function with respect to its input is 1. So instead of 0.25 for the logistic sigmoid, for the 10H, the derivative at the highest point here in the center is 1. So in this case, we have less of a vanishing gradient problem compared to the logistic sigmoid. But of course, it still has the problem of this saturation near extreme values. So here at this point and here at this point we have still this very small or zero gradient, which is still a problem. And this Xavier initialization can act as a small improvement to prevent these extreme values. So how does it work? So it's essentially a two-step procedure. The first step is to initialize the weights from a Gaussian or random uniform distribution. And then the weights in the second step are scaled proportional to the number of inputs to that given layer. And for the first hidden layer, the number of inputs would be the number of features in the data set. And then in the second layer, that would be the number of units in the first hidden layer, and so forth. So here's how it looks like. So assume that the weight is initialized from a Gaussian distribution with mean 0 and a small variance. And let's say this is our weight matrix from this Gaussian distribution, or random, could also be a random normal or uniform distribution, sorry. And then you scale it by a factor of the square root of 1 over m L minus 1. So what is m? M is the number of features, and L minus 1 is the layer index. So L minus 1 means the number of features in the previous layer. So if I have set up like this, and then everything is of course connected to each other. So if I initialize the weights here, I want to initialize these weights here. They are initialized based on the number of features here. And if you didn't initialize the bias units to all zeros, you can also include those in the scaling. But it's fine to initialize the bias units to all zeros. I'm just saying if you don't, then I recommend also including those in that scaling. What is the rationale behind applying this scaling factor here? So that goes back to making an assumption that let's say when we compute the net input, we have a multiplication between the weights and the activations from the previous layer, and you can think of them as independent, right? So, and then if you have an increasing sample size, then the variance of so here I mean if you have increasing number of units in the previous layer, so that's what I'm thinking here of the sample size, then the sum increases because you have independent variables, right? And then you're just adding up the variances. So you can think of it as the variance of the sum of independent variables is the sum of the variances. And then, we have a scaling by 1 over m, where m is the number of the samples, or let's say it's maybe the number of features would be more correct here. And yeah, the square root is to consider the standard deviation. All right, so yeah, here's just a very, very brief sketch of what I meant. So if we have the variance of the net input, so just focusing on one unit here, this can be expressed as the sum over the weights times the activation from the previous layer. So that's nothing new. And yeah, we can, the variance of the sum is the sum of the variances, right? So we can rewrite this. And here I'm just extending it into these are independent variables. And then essentially, because we have a sum over these values and they are the same for all the different positions, right? So I can actually say, instead of summing over these, I can just say it's m times this product in a way. So this is where the m comes from, right? So we are then scaling it back by 1 over m. And since the square root is for the standard deviation here. All right, so but don't worry about it too much. It's essentially a scaling factor. You can think of it more broadly as a scaling factor that accounts for the number of features that goes into a given layer. So that's the main message here, that we take into consideration the number of features. And this is sometimes also called, the number of features from the previous layer, it's sometimes also called fan in, and I have no idea why it's called like that. It's another term that is commonly used. There's actually a term fan in, and there's also the term fan out. I only know everyone is using this like since 10 years ago or something, but I never understood where this name comes from. All right, so in practice, also sometimes, if you look at some initialization schemes, sometimes people also include here the number of output units. For example, they would write it as L here, where L is the output number of features that goes out from that given layer. So that's also something people sometimes do. But yeah, in practice, I think fan in is more common than having both. Yeah, so here's a visualization from the Xavier initialization paper. So what they are showing here is a network with a 10H activation and without Xavier initialization, just for reference now. So here at the top, this is a histogram, a normalized histogram showing the activation value for the different layers in the network. And you can see that in the early layers, like 1 and 2, the activations are more uniform, spread out, whereas for the later layers, they are largely 0. It just happens that how the signal propagates through the network, that we will see in later layers, the activations are more centered at 0. And yeah, consequently, when we do backpropagation, we have this multivariable chain rule, right? So we go usually from the right to the left. So if I have a network, let's say like this, that's the forward pass, and then in the backward pass, I start with layer 5 and then multiply things until I reach layer 1 when I do the updates. So what you can see here is for layer 5s, we have backpropagated gradients that look reasonable in a range, let's say, between minus 0.1 and 0.1. But then the further back I go, I get this vanishing gradient problem. You can see that the early layers almost get 0 gradients most of the time, which can then be a problem. So in this sense, the network will mostly only update the later layers, but almost ignore the earlier layers. So this can be a kind of not good if you want to train a neural network well. So then here's a visualization showing what I showed you on the previous slide, and here a version with the Xavier initialization. So you can see at the bottom, this looks much better. If they use the Xavier initialization, you can see that all the gradients are in a reasonable range for all the different layers. So in this way, that's actually pretty nice. It fixes this issue that some layers learn better than others. All right, so There's another initialization scheme. So Xavier initialization scheme was assuming that you use the 10H activation function. There's also something called a He initialization. So this comes from the fact that the first author on that paper was named his name is Kai-Ming He. And yeah, like I said previously, we assumed that the activations had a zero mean, or mean zero, which is reasonable when we use the 10H activation because it's centered at zero. But for ReLU it's different because the activations are not centered at zero anymore, right? If we have a ReLU function, I will only have positive values, right? Because everything looks almost like a leaky ReLU. Because everything here on the left side, left from zero, will be set to zero, right? So in that way, we don't have the activation centered at zero anymore. So this paper proposes a method that works better with ReLU units where we don't have the weights centered at zero. The activation centered at zero. There's some complicated math in that paper. If you're interested, you can check that out. But the bottom line is that we would add just a scaling factor of 2 here. So in total, we would add sometimes people call that gain. We would add a gain of square root of 2, and we can just put it inside here. So essentially it's just adding a scaling factor, and this addresses the issue with having the activations not centered at zero in the case of ReLU. This is already it. Okay, so you don't have to, I would say, worry about these types of things too much if you just use regular neural networks. So there are reasonable defaults in PyTorch. So this video was more like illustrating that different weight initialization schemes exist. But in practice, I mean, it is a good idea to choose a good initialization scheme, but mostly frameworks handle this automatically pretty well these days. So I will actually in the next video show you how this is done in PyTorch and how we can change the initialization scheme in PyTorch.